Okay, a rigid body experiences a short impact that applies an impulsive force at a point which is a perpendicular distance of d from its center of mass g. The angular impulse momentum equation about g becomes hg1 plus the torque impulses equals hg2. What is the moment within this integral? Well, the only impulsive moment on there would be this impact hitting it, okay? All right, just a quick announcement. I have posted our optional homework assignment, that's number 11. I posted it just as a PDF. It's in our rigid body kinetics linear and angular impulse and momentum module because that's the content of that homework assignment. I will place the solution guide in that same exact module, but you'll notice it's not an assignment because I don't want you to submit anything. I'm not going to grade it. It's completely optional. It's not going to affect your grade one way or another. Braden?
That information. I didn't submit it.
Yes. Yep. But I realize everybody's in crunch time right now, so I don't need to grade it.
I have 2 questions. Not bad.
Okay? Questions? Okay. I want to actually back up to one of the problems we were doing last class because I ended on an uncertain note and I have figured out what I was doing wrong. So let's clarify this problem from last class. It would be great if you could go ahead and turn back to where in your notes we were doing this problem. Everywhere that I'm making like a modification, I'm highlighting it and writing it in red. All right? Actually, let me back up really quickly to part of the notes. At the very beginning of last class, this is the kind of chart that we made. And so we did the linear momentum for a rigid body, and we did the angular momentum for a rigid body if we were finding the angular momentum about the center of mass point G. And then I had a different expression for if we wanted to find the the angular momentum about a point other than the center of mass of the body. We called that A, so any other point. And what I had done is I believe I had went ahead and simplified it for you into the 2D form. Just RMV, where it's a scalar relationship. And for the most part, we really are only going to use the scalar relationship because we're going to be looking at planar kinetics of a rigid body. We're usually not looking at a 3-dimensional rigid body, at least for this section. The same is true for our equations of motion section. We've really stuck to only looking at rigid body kinetics in 2 dimensions, which means that we have usually sum of forces in the x, sum of forces in the y, and sum of moments about the z-axis through some point, right? Exact same thing happens with our momentum equations. We have a linear momentum in the x, a linear momentum in the y, and we have angular momentum about a z-axis that goes through some point, okay? So I think I gave you this one when in reality for the problem where we started to get a little bit confused, it would have been better if I had just given you the straight up vector form of this equation, which is true for however many degrees of freedom you have. So if you have 2 degrees of freedom, this equation holds. If you have 3 degrees of freedom, this equation holds. The vector version always holds. But the fact that it does the cross product takes care of your direction, okay? So what we were doing is getting a little bit confused on which direction certain things pointed, like our velocities and our angular velocity. Okay, so I'm going to end up pulling this equation into the problem that we were working on. Okay, so if we go back to this problem, there's a spool, has a weight of 30 pounds and a radius of gyration. A cord is wrapped around its inner hub, and the end is subjected to a horizontal force, P. Determine the spool's angular velocity in 4 seconds starting from rest. Assume the spool rolls without slip. Okay, what I should have done more explicitly is denote the direction of motion that we were assuming, okay? So in my head at least, it makes sense that if we're pulling P to the right, that this thing is probably going to roll to the left, right? So it's going to start spinning this way, which when it's rolling without slip is going to mean that the velocity of the center point is going to the left. Now, that doesn't have to be correct. If we solve our problem and we get negative numbers, it just means that we assumed the wrong direction, and it's all fine. It'll work out. But we have to assume a direction, and then we need to be consistent about that direction throughout the problem. Okay, so then when we were doing our linear momentum in the x, we needed to specifically keep track of the fact that we assumed the velocity at time 2 was going to be in the negative x direction, right? It points to the left, whereas I've assigned the x direction to be to the right. Okay, so I really did need this negative number here. Then we did the angular momentum about point O, which is the center point of everything. So that's the center of mass. And I needed to be careful about the sign of omega 2. So the assumption here is that all of this is in the k-hat direction. Right? Because this is a planar problem, there's this understanding that this is all happening in the k-hat direction. So omega 2 needed to be positive. So if I look at my coordinate system, x, y, positive z points out of the page. And so then when I roll my fingers in the direction of omega 2, my thumb also points out of the page. So that's positive k-hat direction for omega 2. Then what I needed to check on was the fact that this roll without slip relationship, the way it is written, is a completely scalar equation. It's not assuming any direction at all. It's just saying that the speed is proportional, the linear speed is proportional to the angular speed times the radius. Okay, so nowhere in this equation did we need to be super careful about signs, but in these two we did. Okay, so then if you solve the 3 equations for 3 unknowns, you get the correct answer. All right. And then we did it, I think we did it a different way. Okay, so this is just me solving the system of equations. I went through all of the work to ensure that you get the right answer. And in fact, you do find out, I think, we get a negative omega, which means that in reality, this thing is spinning in the opposite direction than we expected. Totally fine. Just means we got a negative number. Okay? All right, and then we did the second approach where instead of doing linear momentum in the x and then angular momentum about point O, we just did angular momentum about point A, and it turns out by doing this we can solve the entire problem with just one equation. Okay, but when we do this version, we need to be a little bit more careful about using the vector version of angular momentum at time 2. And as long as you use the vector version, everything comes out beautifully. So see again, I assumed the same directions of motion as we did previously. So this is a minus VG I hat. We are assuming it's moving to the left in the x direction. And then my omega is in the positive k hat direction here. Then the cross product handles all of our mashing of negatives, and we get the right answer. Any questions there before I move on? What was that, Samuel?
I couldn't find Tuesday's notes.
Oh.
And I was like, this looks like a homework problem, but it's from recitation.
Recitation, yeah, got it. Okay. I'll post these notes as well so that you can go back and see these corrections later. Okay, so last class was all about the principle of linear momentum for a rigid body and the principle of angular momentum for a rigid body. which means that today we need to talk about those two special cases where we get conservation of momentum, both linear and angular. Okay, so this should not come as a shock to you that when I add the term conservation of, it simply means that the center term cancels out. So if we're looking at the linear impulse and momentum for a rigid body, this is principle of linear impulse and momentum. If and only if there are no impulsive forces, or that those impulsive forces sum to zero, which happens a lot of times when we treat two items as a system that impact each other. If we treat them as a system, the impulse on one body is equal and opposite the impulse on the other body, and they end up canceling. Okay, if this is the case, then we simply have that the sum of the system's linear momentum at time 1 is equal to the sum of the system's linear momentum at time 2. And we call this conservation of linear momentum. Okay, again, this is the special case. It is not always the case that that term cancels, but sometimes it does. Same thing happens for the principle of angular impulse and momentum. If and only if there are no angular impulses, or those angular impulses sum to zero, we get that the sum of the system's angular momentum about some point O at time 1 is equal to the system's angular momentum about some point O at time 2. And what do you think we call this equation?
Conservation of angular momentum.
Beautiful, Annabelle. Conservation of angular momentum. Oops. All right, let's do a problem. To be honest, I suspect that this problem is fairly straightforward, and we've been working with these principal equations for a while, and we know that some things are going to cancel, so I don't suspect that this is any more difficult than our last class, so I'm going to let you guys take the training wheels off for a little bit and work on this on your own. We will go through the problem and maybe write out our knowns real quick. Okay, So the 5 kilogram slender rod, M rod equals 5 kilograms, shown in this figure above, is pinned at O and is initially at rest. So V1 rod equals omega 1 rod equals 0 because we're at rest. And then a 4-gram bullet is fired into the rod with a velocity of 400 meters per second. So mass of bullet equals 0.004 kilograms. Yep. It's fired into the rod with a velocity of 400 meters per second. So let's see, V1 bullet. I'm probably going to go ahead and split this into I'm going to go ahead and write this as a vector. I'm going to go ahead and say that this is 400 cosine 30 in the I hat direction minus 400 both or momenta of both particles and rigid bodies. As long as we do it carefully and use the right type of momenta equations, they sum together beautifully. So in other words, it doesn't mean that we can only use impulse momentum as a system for all rigid bodies and we have to do something separate for particles. They sum together nicely. Okay. All right.
We're supposed to use conservation for this.
Why do you think you cannot use conservation, Samuel?
I just think the other way would be, I just thought not using conservation would be easier. Also, I don't know how to use it yet.
Okay, so the most important trick to start out with is to treat this as a system. Okay, we want to treat these two items as a system because when these two things impact each other, there's going to be a nasty impulsive force that we know nothing about. We don't know its amplitude, we don't know how long it lasts, we don't know anything about it. That's going to apply itself to the bullet and to the board. And so if we only did impulse momentum for the bullet, we would have to deal with those unknown quantities, right? They would show up in the impulse part of the problem. But when we treat them as a system, we have equal and opposite impulses that cancel, okay? So the impulse applied to the bullet cancels with the impulse applied to the board, and we just get that the angular momentum at time 1 is equal to the angular momentum at time 2. Okay. The other question is where we want to sum about. And to be completely honest, I really don't want to have to deal with these reaction forces that I know are at OX and OY at the pin. So ideally, I would like to be looking at summing moments about that point because those don't create a moment at that point. So let's do at O. Okay, so this means that I need to find the angular momentum about O of the bullet plus the angular momentum about O of the rod at time 1. And set that equal to the angular momentum of the bullet plus rod at time 2. Okay, so what we can go term by term here if we like. Remember, we're treating this as a particle. So what is the angular momentum of a particle about some point O? What's that equation? Should be, yeah, Leah? Yes, R cross MV. Where R is is it from the point to the particle? I think. And then for HO rod, what is it for a rigid body? Well, why don't we go back and find that new equation that I just wrote down for us? Well, point O is certainly not the center of mass of that rigid body, right? Point O is just the rotation point. So I think we need this equation here. Angular momentum of a rigid body when we're not summing about the center of mass. Okay, so this should be R O for the rod cross M V G for the rod plus I G omega. Okay, I believe not everything starts at rest. The bullet certainly doesn't start at rest, but the rod does. So I believe this should go to 0. So on the left-hand side, we should just have what will be our R vector. From O to where the particle's gonna sit. It's like minus 0.75 J. Cross with the mass of the bullet times the velocity of the bullet, which we've already written as a vector, haha. Oops. Okay, that's the whole left side here. I'd like for you to think about maybe the right-hand side. Yep. Yep. Yeah, so we want to do the vector from we're looking for the center of mass of the rod, right? Center of mass of the rod should be down 0.5 meters because the whole thing is 1. And we're going from the R vector here goes from the point you're summing your momentum about to the center of mass point. Yeah, so it's from, yeah, we're talking about the rod now. So going to become embedded And once they become embedded, it's just going to be a rigid body doing fixed axis rotation. Okay, so we can draw on those fixed axis rotation equations to say that VG2 bullet should be omega 2, which is in the k hat direction, cross with the radius from the point of the fixed axis rotation to the particle, which is down here where it becomes embedded. So I'm thinking minus 0.75 J. Okay, and then VG2 of the rod is also equal to omega cross R. So omega 2 K hat cross, what is the radius from the fixed axis of rotation to the center of mass of the rod? Minus 0.5 J hat. Okay, so now let's pretend we're going to take this velocity expression, we'll plug it in up here. We'll take this velocity expression, we'll plug it in over here. Something magical happens. I'm then only left with one unknown. Just omega 2. Is omega 2 what it's asking me for? Aha, it is. Okay? So I would like for you to go ahead and try to solve for what omega 2 is. Yes. Here? Yep. Do you want me to erase all my annotations? Okay. algebra issues, or?
I think I might just be frazzled because I don't understand any of the steps that you're doing.
Okay.
I'll just have to look at it.
Where did I lose you?
It might be just a me at this moment issue. I don't
Annabelle?
think you did anything
Can
wrong.
we just assume that they combined and that the difference for the center of the mass of the bullet will be negligible? And just do it as one system after the impact?
That the change in center of mass of the system?
Yeah, like the cross product where you have the mass of the bullet is times 0.004.
Mm-hmm.
So can you just like not do that part because it's adding a small number?
It may end up adding a very, very small number. But generally a good rule of thumb is if they give you a mass for an object, you want to incorporate that mass as precisely as possible.
Yeah. Well, but can you instead include it in the mass of the slender rod? So like when you're doing the slender rod moment, could you do 5.004 or 5? Because technically the two are combined at that point.
Are you saying that this term is tiny compared to this term?
Yeah.
So the problem is that it's not only going to change the mass of the rod, it's going to change the mass moment of inertia of the rod. So my guess is it would be possible to recalculate the mass moment of inertia with that added particle. It's just going to be a lot of extra steps. Right, so this IG is going to be much more difficult to calculate. When, I mean, honestly, this is probably going to be easier to calculate. But your line of thinking is not flawed.
It got the same answer, so.
Yeah. I mean, along your same line of reasoning, if this whole term is very, very small, the likelihood that this IG changes a lot is probably not going to happen. So even if you maybe ignored the bullet after, you might still get a very similar answer. Okay, all right, let's move on. We have the answer up here if you want to try to crunch numbers later. Do you want me to recap overall steps, or do you want me to move on to another problem?
What's the answer?
Oh, sorry. Let's do another problem. That's more fun. Okay. All right, next problem. I chose a fun space one because I like space. The Hubble Space Telescope is powered by 2 solar panels as shown. The body of the telescope has a mass of 11 megagrams. I'll go ahead and write out the known here in case you don't remember that conversion, which I did not. That means that the telescope is 11,000 kilograms. With a radii of gyration of kx equals 1.64 m and ky equals 3.85 m, whereas the solar panels can be considered as thin plates, which is why I've given you the thin plate mass moment of inertias here. Each having a mass, I'll say P for panel, of 54 kilograms. Due to an internal drive, the panels are given an angular velocity of 0.6 j radians per second, measured relative to the telescope. Okay, so omega of the panels is really going to be equal to omega telescope minus 0.6 j radians per second. Okay. Prior to rotating the panels, the telescope was originally traveling at some initial velocity vg. It's interesting that they give you this because you don't actually need it. You don't actually need to know that. You may neglect its orbital rotation. Okay, so that just means that even though this thing is probably orbiting a planet, probably our own, or actually not our own, Hubble's way out there, ignore the fact that it has gravity pulls on it by different planets. All right, determine the angular velocity of the telescope due to the rotation of the panels. So just out of curiosity, maybe a thought process here. Do you think the angular velocity of the telescope will be greater or less than the angular velocity of the panels? Why do you say less than?
Because the mass of the telescope is way bigger than the
100%. Absolutely. For momentum to be conserved, these two things need to equal out, right? And so the mass of the telescope is massive. It's huge compared to those panels. So even spinning it at a little rotational velocity is going to have the same momenta effect as the panels. Okay. So let's go ahead and maybe compute I, G, Y for the panels. Which equation do you think, if we compare the image of the telescope on the top to the equations down on the bottom, which axis do you think I care about for my mass moment of inertia? The X? Yeah, I think that's a great idea, especially if we treat B as that, which length here, the 6 meter or the 1.5? The 6 meter, yeah. So I'm going to grab that X equation, which is 1/12 m B squared, B being that 6 meters. Okay, and my mass here of the panel is 54 kilograms. So I can go ahead and figure that one out or just leave it as it is. But it's just a number. Okay, asking us to find omega 2 of the telescope. Okay, so when it tells you that they talk a little bit about like prior to the panels rotating. So what I would like for you to do is consider all the angular momentum to be 0 at time 1 and to be non-zero at time 2. All right. It also appears to me that all of the rotations that we're talking about are about a single axis on the telescope picture. What axis is it? I heard it whispered. Yeah, I agree with you, Micah. It's Y, right? So that axis is the axis that's rotating these panels. And it also goes beautifully through the center of mass of each panel and the center of mass of the telescope. Okay, so that makes me think that a good conservation equation would be one that's finding the angular momentum about this y-axis going through point G of the system. So conservation of angular momentum about the y-axis going through point G of the telescope, or of the telescope system. So that looks like the sum of all h y1 equals the sum of all h y2. where I'm summing both the momentum by the panels and the telescope on both sides. So HY1 panels plus HY1 telescope equals HY2 panels plus HY2 telescope. Okay, notice this time I did not write vector bars because we are only going to analyze this about a single axis, just the y-axis. Okay, which means that we'll use the reduced form of for H for a rigid body, the scalar form, which is I G omega. Because luckily y goes through G of both the panels and the telescope. All right, and I said at time 1, there's no momentum. I'm gonna leave you there. Try to stew on that for a little bit. Okay, so we had a question about, we have IG for the panels. We solved that right up front in the known. But the IG for the telescope is a little less straightforward. We would need to grab that radius of gyration about the y-axis, that 3.85, and interpret that. So we should remember G equals square root of I G over M. That's our radius of gyration equation. If this is 3.85 squared times 11,000 kilograms, that should be our IGY for the telescope. Okay, don't forget there are 2 panels. Okay, just like we predicted before we even started the problem, we get a very, very, very small rotation by the telescope. So some 10 to the minus 3 radians per second. Why is it negative? Does that make sense? Well, the angular velocity of the panels was 0.6 J.
These counteracts the.
Yeah, it needs to counteract, right? Like the only way for these 2 terms to equal 0 is if they cancel each other. So one's got to be positive and the other one's got to be negative. So one rotation by the panels results in the opposite rotation by the telescope. Okay, let me do some final announcements for the course.
I got a much smaller answer.
A much smaller.
I got times 10 to the negative 6 for something. But I know it's wrong, so
You do know what's wrong. Yep.
I know something's wrong. Just not.
Internal moment, is it one of the 12
Probably about that.
4 times 6, or is it supposed to be 6 squared?
You're talking about the mass moment of inertia of the panel?
Yeah.
Oh, sorry. Yeah, there is a squared there. That's a great question.
That's a question.
Yep, I forgot the squared. Thank you. Which comes out here as well. Okay, I got one of you wanting to scroll up and one scrolling down.
No, he was just making a joke. He was
Oh.
referencing something.
I'm referencing, yeah, it's a
He was
reference.
referencing something.
Gotcha.
It wasn't funny.
It wasn't fun.
Well, now I'm laughing. Okay, last announcements for the course. Today is obviously the last day of this week. We have one more week of class. That's it. And then we have the final. So next week on Tuesday, I am going to cover rigid body impact. So Tuesday, rigid body impact. Thursday, our final Jeopardy review.
Just get an A on the exam.
Then we have our final. Yep, question, Andrew?
Could there be like a reward?
Recitation.
A reward for, what do you want me to get? Do you want me to get candy or something on the exam, I'm sure?
I prefer grading.
I don't know. If I won the Jeopardy, I know what I'm doing, so I don't even need to take the final.
I'll think about it. I'll consider it very deeply.
Yeah, the bottom, they get
No negative reward. Question?
When is the final?
That's a great question. I think it's on Thursday of that week.
I have it on Thursday. What the heck, bro?
Say again?
Thursday, 10 to 12.
She has memory.
Thursday, 10 to 12.
Is it in here?
As far as I know, yes.
Is anyone showing up to my EE exam Friday at 6?
Final exam, Thursday,
Can you be there for most?
10 a.m., 12 p.m. here. I will have recitation next week. Yes. Everything is fair game. Everything is fair game. Hadassah? I will release a practice exam. Yep.
When you release the exam,
No.
That'd be nice.
Any other questions?
you need to tell us it's the exam. Just say it's the practice exam.
Okay, my textbook is floating around here somewhere. If you, yes. If you need the textbook for your redemption assignment, you're welcome to grab a look at it right now.
I gave it to you back like an hour and about 10 minutes.
My focus is so limited when I'm teaching.